So this is an interesting room, right? I feel a little bit like this is dinner and a lecture, right? And the servers are going to come around and bring your meal while this goes on. I'm very honored to get to do the Pritsker lecture. As I'll tell you a little bit during the talk, Alan was a big influence on my life and my career after I left here as well. This talk assumes no background in simulation whatsoever. There is zero mathematics in the talk. I'm going to tell you about this long-standing problem and how we're evolving in our thinking about it. But whether you've got any background in this topic at all, I think you'll be able to understand what it is that we're going to do. So a little bit about Alan. Well, you have to turn the pointer on. So my first encounter with Alan was in IE 580, Systems Simulation, in spring quarter of 1980. Now, I think this was either the first or the second time that the class had been taught with SLAM. Does that seem about right, Gene? Because the SLAM book was 1979 that it came out. And it was a case-based course for master's students, meaning we worked on simulation projects, wrote reports about them as we went along. And SLAM was new and revolutionary at the time. And lots of the concepts that you see in modern languages really originated with SLAM. So you had network modeling, and this is what this was the first SLAM network model that I ever saw, which was the first model in the book. So you could do network modeling, where you thought of it as entities flowing through a network like the languages you're using now. But you could also seamlessly integrate with discrete-event programming with simulation and continuous time modeling, that is differential equation models that describe a continuous process of value seamlessly in one language, and it was fully integrated with Fortran. Well, it was Fortran, right? And so it compiled as a Fortran program, so it ran fast. And that was something that was always important to Alan because he knew we would always want to do bigger and bigger models. Now, you didn't get this on the screen. You drew this with your IBM flowcharter template, and then you wrote code like this to actually run the model, but that was a forerunner of the kinds of things that we do in simulation. It was a great class, and it really influenced my master's thesis, which then influenced what I did for a dissertation. So today, as many of you know, a simulation looks something like this. So here's a simulation model of the security at an airport check-in. First of all, you can see it isn't something you draw with your IBM flowcharter template, right? It's a graphical model. It's built graphically, but also is animated, which makes it much easier to tell people about what the model is supposed to do. And you would use a simulation model like this to be able to, for example, decide how should I staff my TSA security check-in in order to get people through efficiently. In fact, a project we did in my class right when TSA Pre was introduced was to say how much additional delay are the people that are not TSA Pre going to be when we siphon off these channels for the special folks who are willing to pay $85 for TSA Pre. And that's what simulation is good for. You can build a model to whatever level of realism that you want, and then you can perform experiments on the model instead of performing experiments on the real system. And Hong, this is what you teach now? Yeah, so you teach simio.
And students continue complaining the people walk funny.
Yeah, so it's realistic to a point. So behind the pretty animation, it's important to say really a little bit about what's going on. So first of all, this kind of simulation is really good when the world is thought of as being stochastic, not entirely predictable. So when we run a simulation, we see realizations of the random processes and we see the kind of realistic behavior. Right? TSA security doesn't look the same every Monday. Right? Sometimes it's more congested than others, and there's a certain stochastic nature. The systems are dynamic and often time varying. And so the business people come in the morning to the airport, there's a big rush, then there's a lull in between, and then maybe the leisure travelers come later, so it's not, in general, a stationary process. Now, one thing about simulation is you can't sort of take derivatives and set things equal to zero, and the kinds of stuff that we can often do with mathematical models, we can simulate instances. So give me a particular configuration of the number of people working security, the number of check-in kiosks, and so on, and I can simulate it and see how it performs. And I'm going to come back to that point. And it may be computationally expensive. In my own experience, sort of my worst case of this, we were doing a project of simulating a fuel injector assembly line for Delphi. This was a brand new $20 million bet the company sort of thing. And to simulate 20 days worth of fuel injector production took us 8 hours on a pretty high-end PC. Right? So sometimes the models could be pretty expensive to run. You didn't just instantaneously get results. And it's blackish box. I mean, I built the model, so I certainly know something about what's in it, but often I don't know nice mathematical properties that might help me to be able to optimize it or do something like that. So we sort of treat it as a black or a blackish box. Now, as Avi said, I was extremely fortunate to be at Purdue at the time that we were having this tremendously rapid progress in simulation, applications, and research, not just at Purdue, but nationwide. Purdue was leading it in many ways, but it was really... So here are the things that were happening. It's hard for you to believe today, but we were just migrating from simulations run on the big CDC Mace mainframe here at Purdue to running them on workstations to PCs. That migration was just beginning. Avi also mentioned spin-off companies. So Alan spun off a company, Pritsker and Associates, from his work on simulation. It was the first one I had ever heard of a professor doing. And the point was to both develop software and provide consulting on people on this emerging technology of simulation that was really becoming popular to solve realistic problems. Some people might not remember that Randy Sadowski, who was a faculty member here, was one of the first people to work on a graphical model building environment for a different product called Blocks, where finally you did drag and drop things on the screen as opposed to drawing them with your flowchart or template. And that happened here as well. And then Bruce Smizer, who was my advisor for my PhD, and a number of other people, were putting together the science base of what we now think of as simulation. Thinking of it as a stochastic process or as a statistical experiment, and really moving computer simulation from being a computer science modeling sort of discipline to also having this underlying mathematical description, which has paid tremendous dividends over the years. When I talk about simulation, I say simulation is used for three things: feasibility, sensitivity, and optimization. Feasibility is just, hey, if I do what I'm planning to do, will it actually work? Sensitivity is, well, I don't really know everything about how the components of the system. How sensitive is it to things that I'm not really sure about? And then optimization is what you think, right? I want to optimize the performance, say, of that airline security system that I showed you, using the simulation in some sense as the objective function. And the topic I'm going to talk about today fits there in the optimization category. When I was here in 79 through 83, we were just beginning to think about optimization. A lot more of it happened just after I left. So what are we going to do? Well, we borrowed from other disciplines, right? We didn't really have a simulation version of the problem. And the very first question you have to ask is, what should we optimize? Right? I can't optimize that airline system so that every day, no matter who decides to come or what rush hour I get or what person leaves their liquids inside their suitcase, that on every day it's the best that it could be. Right? That's not possible with the stochastic system. You have to pick some summary or performance measure to optimize. And we tended to do long-run average performance. So that tends to be a very common to say, nope, day to day it's going to be variable, but long-run average or expected value of performance, and that's kind of where we started. We sometimes think about other things now besides that, but that'll be good for what we're going to do today. So we wanted to beg, borrow, and steal. So one place that we could borrow from was response surface methodology, which is being used for optimizing industrial processes by statisticians. Basically using regression models to find better and better settings of the things that you can control, running a sequence of experiments to try to find the optimal value. And my former PhD student, Jim Swain, we all really respected Jim. He showed up for the PhD program having already written a book with Bill Biles, which was one of the first books to say, you know, we could take this response surface methodology and use it to optimize simulation models, because after all, they are statistical experiments. So that was one of the places we started. Then, of course, there were lots of heuristics for optimizing tough sort of black box kinds of problems where you didn't assume much. So naturally, those were things we could do too. Things like Nelder-Mead and various kinds of pattern search were sort of a natural to think, okay, let's see if we can adapt that to optimizing the performance represented by a simulation. But the one I want to talk about today is the area of ranking and selection. So ranking and selection, from an optimizer's point of view, is not optimization. It's complete enumeration. Right? I'm going to simulate every single alternative. Now, this was started in the statistical field, actually, by Shanti Gupta here at Purdue and Bob Beckhofer at Cornell, for biostatistics kind of problems, right? I've got 4 drugs and a placebo, and I'd like to run trials with real human people and find out which of these has the best effect, for example, in terms of curing. Well, Dave Goldsman, who came here on sabbatical with Lee Shrubin in about 1981-82, in addition to doing simulation work with Lee Shrubin, had also worked with Bob Beckhofer on a lot of these ranking and selection problems. So it's very natural for Dave to say, 5 drug treatments, 5 different designs for the airline check-in system. Why can't I take this idea from ranking and selection and apply it to the simulation context? Right? Now I'm simulating systems instead of running physical experiments, but it's kind of the same thing. And he wrote a very influential tutorial in 1983 in the Winter Simulation Conference, and people started to notice this idea, although we didn't talk about it as optimization in those days. And the thing we liked about ranking and selection is pretty weak statistical assumptions behind it, so you didn't have to have really strong assumptions to make it work, and you had a statistical guarantee at the end. You could say something with statistical rigor about, for example, the chance that you had actually found the optimal solution, or how far you were from the optimal solution. That was very appealing because we couldn't do that much with these other kinds of methods. So my talk today is going to focus on this ranking and selection context where you actually simulate everything, which sounds like it's easy, and I'm going to try to convince you on this next little demonstration as to why it's hard. Oh, and I forgot about this. This was a paper which was very important to me. Dave Goldsman, myself, and Bruce Smizer had a 3-way public argument about the best way to select the best system. And Dave did ranking and selection, and I did something in the area of multiple comparisons, and Bruce Smizerized it. That's all I can describe. He had his own way of doing it, and if you were Bruce Smizer, you could make it work. And we got up in front of people, and we worked on a common problem, which was very computationally difficult to do, and we argued about the best way to do it. And the thing is, at the end, I was convinced that Dave won. Right? That was really when I converted to saying, you know, the ranking selection paradigm really is kind of the right paradigm for thinking about this problem, although I would have claimed at the time that I did fine. Really, in my view, Dave, and what's happened afterwards, I think kind of demonstrates that that's been the case. Okay, so I want to do one little demonstration today. This is a spreadsheet that I often use when I want to talk about simulation optimization. So let's think about that airline check-in system. And let's suppose I'm trying to minimize the long-run average time that people take to get through security. And it turns out, if I can put my pointer so it doesn't hide things, in this one, I've got 10 alternative designs for the airline check-in. So number 1 through 10 across the top. Now, they have a true long-run average time to get through, which I don't know, but those are in the second row. So if I'm trying to minimize, alternative number 8 is the best. But of course, I don't know that. I haven't run the simulation yet to be able to do it. And so the blue diamonds, those are the true long-run average responses for those 10 designs for the airline system. Now remember, you get to be a clairvoyant and know what the right answer is, but in practice you don't. You have to run the simulation. So every time I press the ranking and selection button, it's going to simulate 2 observations from each of those systems and take the average of them. Then I'll press it again, it'll simulate 2 more replications. You can think of it as 2 more days of check-in, and now I've got the average of 4 observations, and then 6, and so on. And I want to talk to you about why even ranking and selection is hard. So I push the first time, and the crosses, those are the averages. So those are the average of the 2 observations from each of those. So for example, this cross right here is the average from true observations whose true value is 17 for the time to get through the system. Which one do we think is the best at this point? Number 3, right? Is number 3 the best? No, right? Its true long-run average is way up here. So, yeah, it's noisy observations. I haven't averaged very many of them. So I've made a mistake about which one is the best. Suppose I stopped at this point and I implemented number 3. Would I be disappointed in how it actually performs? Yeah, because this average is down below 5 minutes and the true average is above 15 minutes. So these are the 2 kinds of errors that come up. One, if I've got too much statistical error, I don't pick the one that's truly the optimal. And secondly, I have a bias for thinking that something is better than it is, because I'm picking the one with the smallest average, right? So I've got a bias of being optimistic. Now, of course, as I continue to add observations, so you might want to track which one we think is the best at each case. So now we have 4 observations. Which one do I think is the best? Right, system 7. Am I optimistic about how it performs? Yeah, right. I think its performance is something like 3 or 4, and it's really up here at 15. I actually, at this moment, have a pretty good estimate of how good the true optimal is, but I don't realize it's optimal. Right? And of course, that was just by chance. And so let's look at a few more. Okay, and so I've got 6 observations, and I'm still wrong, still wrong, still wrong, still wrong, but I'm getting closer. And right about this point, if I stopped, I might pick the one that's actually the best. If I do one more, I'll be able to do that. Now remember, you knew where the blue diamonds were. But if it's a real problem, you don't know where the blue diamonds are. And one of the things ranking and selection tries to do is say, when can you stop? Right? When have I taken enough observations that I have something like this? And I picked the right one. Okay, so that's your brief, quick introduction to ranking and selection. I also use this spreadsheet to illustrate globally convergent and locally convergent algorithms. If you ever want the spreadsheet, just send me an email. I'm happy to send it. What the remainder of this talk is I want to explain to you how we got to our current state of knowledge in ranking and selection, and where I think we need to go next. And the work on where we need to go next is work I'm doing with Professor Susan Hunter and my PhD student, Linda Pei, right there, who's hiding. She knew she was going to get mentioned here. But look, ranking and selection is a math stat kind of exercise, and if I really explained it, none of us would be happy. So for the next 20 minutes, I want you to pretend with me that you are the world's greatest super spy. Right? You are the world's greatest super spy. A cross between James Bond and Kim Possible. Right? That's who you are. Now, every super spy has an arch nemesis. Right? How can you be a super spy if you don't have an arch nemesis that you're after? Your arch nemesis is Raghu the Jackal. Right? Not Raghu the Pasupati, Raghu the Jackal. And you have been chasing Raghu the Jackal for years and years and years with no luck. In fact, nobody's ever seen Raghu the Jackal, such an arch criminal he is. But suddenly, on the dark web, we get a break. And the break says, Raghu will be at a dinner party next Friday. So not tomorrow, but a week from tomorrow. And there's one interesting characteristic. Raghu is always the shortest person in the room. In fact, he prides himself on the fact that despite his small stature, he is this master criminal. And he makes sure, in any event where he is, that he is the smallest person in the room. Now, he probably surrounds himself with other short people so as not to be able to be easy to distinguish, but that's the approach. So, Your mission is to find and capture Ragu as quickly as possible without creating an international incident, right, by taking the wrong person. All of our assets are at your disposal. Good luck. Okay, so you're the world's greatest super spy, and so your organization says, how do you want to go about it? And because you're very, very smart, you say, well, first of all, how many people are there going to be at this dinner party? Right? That's kind of a reasonable question. So based on our scouting so far, we think it's going to be kind of like this. And apparently they're all going to be in period costume as well. But there's what the dinner party is going to be. It's going to be a relatively small number of people. And so you say, okay, I'd like for Q is your gadget person, just like in James Bond, creates all the neat gadgets you need. Have Q create a laser belt buckle that can take measurements of height. Right? And what I'll do is go around the room and take multiple measurements of these people until I've got enough measurements that I feel like I can tell which person is the shortest person in the room. Now, why do I have to take multiple measurements? Why not just one measurement of each person? Well, people don't stand still. Right? People move around like I'm doing here. They may bounce up and down, right? They may be leaning over. So I can't just take one measure to be sure. In a statistical context, we call that variance. So thinking back to the TSA security problem, that's the fact that there's variability about when people arrive to the airport, what they've got in their luggage, whether or not they have to be pulled aside for separate screening. So there's variability, and variability means that I need to take multiple measurements. Now, one of the first big breakthroughs in ranking and selection, back before it got to us in the simulation world, was to say, we can account for the fact that there is variance and that I don't know what the variance is. Right? I don't know how much somebody's going to move around. Some people move a lot, some people move a little. So ranking and selection was able to say, I can both estimate the variance and take the observations that I need and know that, for example, I've measured people so I can tell differences of 1 millimeter or less. Right? If that's what I think is going to be precise enough. So that's great. That's exactly how I'm going to solve this problem, or you're going to solve this problem as a super spy. Going around the room, getting enough measurements, letting the procedure tell me when I've got enough measurements on each person to stop. Now, one thing I want you to notice about this is that's really nice is there's no coordination required. Right? I can measure one person, I can go and measure another person, and I don't have to coordinate between them. And at the end, when I'm done with all the measurements, the one that has the shortest average measurement, that's the one I'm going to pick as being Ragu. So it's a really nice, simple procedure. You go home that night to your luxury apartment in Manhattan and say, I've got this problem whipped, we're going to catch Ragu the jackal. Then you come in Tuesday morning. And they say, oh, we've got an updated idea about the size of the dinner party. We think the dinner party is going to look more like this. And you think, oh my goodness, there's no way in any reasonable amount of time that I'm going to get around the room and measure all those people to a level of precision at which I can tell at the end that the one with the shortest average measurement is the shortest person in the room with high confidence. So what am I going to do? Well, you didn't get to be the world's greatest super spy by not being brilliant. And so what occurs to you is, I don't actually need to know what the height is of the shortest person in the room. I just need to know who is the shortest person in the room. So you say, okay, have Q modify my Google Glass so that I can look at two people and measure their difference in height. Right? That's pretty easy to do for me to look at a couple of people side by side. And the difference could be positive or negative in their height. And again, because people move around, I may have to take multiple measurements. But as soon as I decide that Professor Hong Wan is shorter than Professor Susan Hunter, I don't have to consider Professor Hunter anymore. Right? I can eliminate her as being a suspect, and I just have to keep Professor Wan as a suspect. And I've always suspected her anyways, so that's fine. So this is a huge insight. We only need to look at differences in height, or, for the airline security system, differences in time to clear security. I don't actually have to know what the actual time is. Now, in the worst case, this could be quite bad. if I have K people at the dinner party or K different designs for the airline system, there's an order K squared comparisons that I would have to make, but it's not going to be that bad. Because pretty quickly I'm going to eliminate tall people like Professor Hunter, and I'm going to get to the people who are short pretty quickly, and therefore I can do more work on them to be able to tell the differences. So this is enormous. This will allow me to potentially go around the room and be able to do it. Now, one thing I want you to notice, though, is now there's some coordination involved. Unlike the first approach where I could measure each person individually, now I'm looking at pairs. And I'm sort of saying, what the differences are in those pairs. So no longer is this an uncoordinated exercise. Right now I need to be able to coordinate things. But that's fine. Right? That's going to work okay. Okay. All right. Problem solved. Go home on Tuesday night. And you know what's going to happen on Wednesday. Oh, it's going to be even bigger than I thought. Right now I've got this room packed full of different people, much bigger than what I thought. What am I going to do? Now this is kind of where the simulation community came in. Right? The basic ideas I've talked to you about up to this point were known in the ranking and selection statistical literature. But we in simulation wanted to go to much larger numbers of designs of the airline check-in system or people at the dinner party and still be able to do it. But we really like this idea of looking at differences. So what we did was say, we just have to get more clever. So we might say, hey, what I'm going to do is I'm going to grab a short-looking person. I'm going to kind of walk them around the room for a while and see people that I can get rid of, right? Like this guy right here who stands up way there, right? I might be able to do that. Maybe I'll set up a free photo booth where I can get people to stand side by side, very straight and very still, and so only a measurement or two will be able to tell the difference, and on and on. So what we did was get clever. So as I said, we really like this idea of looking at differences, but what we did in simulation was soup it up, right? Do lots of clever ideas to make it scale to bigger and bigger problems. So screening is saying, let me use some really rough tool to get rid of a bunch of these airline security designs or people in the room, whereas I don't have to measure things very precisely just to get broad brush, get rid of a bunch of them. In simulation, we control the source of randomness by the random numbers we use in the simulation. So maybe if I use the same random numbers when I simulate each airline check-in version, that's kind of like getting people to stand really still side by side in the photo booth. Right? I've cut the variability of the difference between them. Recently, we've used a lot of ideas from statistical learning, sort of Bayesian reasoning, to say, hey, let me consider everything that's going on there and say, what measurement would be the most valuable for me to take next to be able to distinguish the shorts from the talls? And kind of on and on and on. We've been really good at this, and we've been really busy at it for a long time. So as I said, for the last 20 plus years, we've been squeezing more and more and more efficiency out of this paradigm, right, by doing lots and lots and lots of tricks. Now, those tricks involve lots of coordination, right? Everything I talked about there was more and more coordination of my activities, more and more comparisons that I'm doing, more and more updatings of things. But hey, if it's number of measurements I'm trying to cut down that I have to take, that works, right? If that's my primary goal, is to figure out what Raghu the Jackal is with the smallest number of measurements, then all of that makes good sense. So surely we're done, right? Surely it can't possibly get worse than this. And then on Thursday's update, it looks like that. Yes, Waldo is right up there somewhere, right? So now it looks like, where's Waldo? Curses. It looks like Raghu the Jackal is going to escape us again. There is no possible way that we are going to be able to measure, look at differences. Even with all my tricks, I can't possibly get to that point with that many folks that I can do it in less than 2 weeks and the dinner party will be over. So Susan Hunter and I call this the ranking and selection limit. We've reached the ranking and selection limit, and now we have to think about doing something else. Ranking and selection is really appealing because I do get this nice guarantee at the end, and I've looked at everything, so sort of no matter how perverse the response surface is or the objective function is, I should be able to control things because I look at everything. Now, I'm not going to talk about the other things we could do because I'm going to try to think differently about ranking and selection. But you might wonder what we would do in the simulation community. And you have one of a local expert, Professor Pasupathy. We might say, you know, it's not as bad as that picture. There's probably some spatial relationships, right? So maybe tall people tend to be sort of congregated in some parts of the space, and short people tend to be congregated in others. And if that's true, I can use that spatial relationship to at least try to quickly find a really, really short person in the room. I don't have the nice guarantees of ranking and selection if I don't look at everybody, but I ought to be able to exploit that. And of course, lots of real problems have exactly that sort of structure. But if I'm worried about causing the international incident, well, yeah, maybe not so good to do that. But then our gadget guy Q rushes in and says, what if I can give you parallel bonds? So what do we mean by parallel bonds? Well, that means we've got all 6 of the James bonds, and I'm going to give you more people to work with. And they can work in parallel, right? They can take parts of the room or whatever strategy we decide and be able to cover more of it. So it's going to now be 7 super spies, you, Kim Possible, and the 6 additional James bonds, and you're going to try, even in that Where's Waldo setting, to see if you can do it. So we're going to increase the ranking and selection limit by working in parallel. So how's the best way to use the bonds? Well, the first thing that might occur to you is, hey, divide the room up into 6 pieces, send the bonds out to each piece of the room, let them find the shortest person in the piece, and then we'll compare all of those at the end. And it's not a bad idea, right? But if there really is some kind of spatial structure, I might waste Roger Moore on looking at an area of the room that's all tall people. He's going to waste a lot of time trying to find the shortest of these tall people that's not nearly even going to be competitive in any way, shape, or form. And then just having parallel bonds introduce any new statistical problems. Right? This is suddenly a different problem because I'm, from a statistical point of view, because I'm now working in parallel. So parallel computing is the new frontier for us in ranking and selection, or simulation optimization in general. Everything from multi-core laptops, like that laptop there has 2 cores, each with 2 threads, so I can run up to 4 simulations at a time, to local clusters, to commercial cloud services like Microsoft Azure and Amazon Web Services. In fact, one of our simulation languages, the one I demonstrated to you, already links with Microsoft Azure, and they claim you could recruit up to 10,000 processors simultaneously. Turns out the latency to recruit 10,000 processors is a long time, so you probably don't want that many. But a couple hundred, all right, no big deal. And so now you've got a couple hundred bonds that can work in parallel. And since simulation optimization, or simulation is about simulating instances, measuring a particular person, or simulating a particular design for the TSA security system, those parallelize wonderfully. Put one simulation on one processor, put another simulation on another processor. They don't have to be connected to generate those observations. I have to coordinate eventually at the end. But in terms of simulating, I can really take advantage of parallel computing. Right? It's not like inverting a matrix, which is one big operation I've got to figure out how to break up. I just put different instances on different processors, for example, and go from there. Or different replications on different processors. All of that can be done. Now, you remember I said a minute ago that all of the tricks that we had been doing was about decreasing the number of observations that are required to be able to find Ragu the Jackal. But now in this parallel computing environment, particularly when I think about the idea that I'm paying for these processors, or I can't just tie them up forever, what does efficient mean now? So that's one of the first changes. So here's the way I want to think about my parallel environment. There are other ways I could do this, but each of these greens are one of the bonds, so those are the worker processors, right? So think of them as computer processes or as my bonds. And then I'm going to pull off one particular processor, this purple one, which is going to be called the master. And the master is sort of the decision-making processor. And each of these symbols here, geometric symbols, is a job. And the master is kind of creating jobs, making decisions about the jobs, sending them off to the processors, and the processors are doing it. Now, in the framework that Professor Hunter and I propose, we think of a job as consisting of up to 5 things. Which systems I should simulate, like which particular airline design for the check-in I should simulate. How much should I simulate it? How many observations should I get? We get a choice about random numbers, so which random numbers should I assign to this? And particularly if I've got calculations to do, what jobs do I have to wait to finish before I can do the calculations that I need to do? All right, so everybody sort of understand the environment. These jobs are going to circulate in the system. They might be doing simulations on the green processor. They report something back to the master. The master makes decisions and sends them out. And these guys could make decisions as well. But this is just sort of one way to think about how we might do it. So what can go wrong? Lots. Lots of things can go wrong. So a very natural thing to do is to say, use the worker processors for simulations, let all the comparisons be done on the master. The master can make decisions about who to eliminate and which additional jobs need to be done. But if the master is being overwhelmed with reports back from the workers and has something on the order of k-squared calculations to do the competitors, to compare the competitors, pretty soon the master can become overwhelmed, and the worker processors are sitting idle waiting for the master to tell them what to do. Right? So if I just do that naively, that's not going to be a very good idea. There's now a load balancing issue that didn't come up before I had parallel bonds. What if the simulations don't all take the same amount of time to execute? Right? I'm simulating 2 different settings for the airline security system. One of them reduces congestion quite a bit. Maybe it runs faster than the more congested simulation. Or maybe the processes are heterogeneous. Or maybe there are message passing delays. There are all kinds of things that could mean that each simulation job, just like each measurement for the bonds, might take different amounts of time. So now my sample sizes are random and unequal, which is not what I usually assume in the ranking and selection procedures developed in statistics. Right? We typically thought we can control the number of observations and set what they are. This is a subtle one that's really important. What if the result I get back from the simulation, the amount of time it takes, is correlated with the value I get back? If the airport is really congested, the simulation model takes longer to execute before it reports back a really long waiting time. Whereas if it's a particular replication where the airport is not congested, it comes back quickly. Oh, now the order in which my data comes back to me from the workers is not independent and identically distributed. Shorter things come back faster, longer ones come back slower. That also violates almost everything that I assume. Right? So the data in the order realized is no longer IID, but now if I wait to synchronize it, okay, what have I done? Right? Now I've lost processing capability because I'm waiting. And I'm keeping things idle while I do that. I've got bonds standing in the room saying, what do I do next? What do I do next? What do I do next? Right? And I'm not getting any benefit from it. And finally, and I put this in gold because it's the gold standard in ranking and selection. In ranking and selection, we often say, I want a guaranteed probability of correct selection. A guaranteed probability that I find Raghu the jackal. That is an objective that does not scale. It's a family-wide statistical decision which involves all of the people in the room. And therefore, the more people that there are in the room, the more I have to simulate each of those alternatives. not just the fact there are more people, but each of them has to be simulated or measured more to control that. It does not scale. Right? It is not an objective that scales well to bigger and bigger processes. So, old think, new think. So, along with Linda Pei and Professor Hunter, we're working on rethinking this problem. So, statistically efficient versus efficient. Now we've got to think about computing capability, not just number of observations. And we can think about a fixed precision, where I want to reach the desired conclusion with as little computational cost as possible, sent to Amazon or Microsoft. Or fixed budget, which is I'm going to buy this much processor time, and I want to get the strongest conclusion that I can get in that processor time. But we can no longer ignore computational cost, because it's not just all about number of observations. I'd be willing to take more observations if it was less costly for me to run the procedure. Probability of correct selection versus what? So as I said a minute ago, probability of correct selection becomes more and more and more expensive the more alternatives you've got. If I've got 1 million plus alternatives, do I really want to drive this in order to find one particular one? Well, maybe with Ragu, the Jackal, I might want to do that. But in general, in an industrial problem, I might like to very quickly find the good ones, the ones that are worth considering, and get rid of a lot of the others very fast and very efficient. So we're going to propose, as one objective, false elimination rate, which says the rate at which I throw away good designs for that TSA system should be controlled. Right? And that's going to come to scale up. Okay, we call this parallel adaptive survivor selection. What does it mean in terms of the bonds? Each bond gets an earpiece, a laser belt, and a 6-foot stick. What do you do with the 6-foot stick? Well, we're going to assume Ragu the Jackal is less than 6 feet. This is the shortest person in the room. It's going to be less than 6 feet, right? So there are the bonds with their earpiece, their stick, and their American Pride belt buckle. Now, as they walk around the room, they eliminate suspects by comparing them to the stick. You know, and the stick doesn't move. It's a set height. It's pretty easy for me to make maybe one or two or a few measurements and tell that somebody is definitely taller than the stick, or I can't tell. Right? They appear to be shorter, but you know, I'm less sure. But I can definitely tell that they're taller. You, as the super spy, are not doing with the stick. You've got the central earpiece, and every so often they're reporting back to you a few measurements on the people they couldn't get rid of. Right? So here's somebody that I can't say is taller than the stick, and here's a few measurements that I got. And you're keeping a running average of those. So you're keeping a running average height, an estimate of the average height, of the people who have not yet been eliminated. That's going to be kind of somewhere in the middle of their heights, right? What we're going to do. And every so often, you tell the bonds to break off their stick at a new height, the current average. So you say, now, all of you break off your stick at 5'6". And now they start going around the room, right? And they start eliminating people, reporting back to you about the people they can't eliminate. Now break off your stick at 5'1". Right? And we keep working our way down in that way. Almost no coordination whatsoever, which is kind of what we're trying to get around. And finally, when there are a few suspects left, now you're going to do your precise measurements and try to figure out who Ragu the Jackal is among those ones that are left. So that would sort of look like this. Each job now relates to either a design of the TSA check-in system or somebody in the room that I'm trying to measure. And I send them out to the workers, to the bonds, and say, measure this person for a while, and if you can eliminate them, boom. I don't have to consider them anymore. But if you can't, report back to me the average measurement that you got. The master has almost no work to do. The master is just updating this average as the information comes in, and every so often deciding to set out a new height, or what we call a standard that we're going to do. So the master shouldn't get overloaded. Has almost no processing to do, and I can keep the bonds busy all of the time. So this is a paper we're going to be presenting in this year's Winter Simulation Conference, and we can show that under some settings, we can control the false discovery rate without having to increase the number of measurements per person, the number of simulations per airline check-in design, even as those numbers go up to the where's go low level. And we've avoided the coordination, which is what slows the parallel ranking down, and we've proposed a new measure of a way to think about what the ranking and selection procedure would do, which scales to larger and larger alternatives. So I would claim that thinking this way comes from many things that I learned from Alan Pritsker. So I want to talk to you about 3 things that I learned from Alan Pritsker that have very much influenced my career. The first was, the best way to find holes in your thinking is to write. Alan told me that very early as a PhD student. Alan was a prolific writer. Those are the 8 books that I was able to grab off of my bookshelf and fit in one frame of the picture. Alan wrote many more. Somebody took my first edition slam book, and I've always been very bitter about that. But Alan wrote all the time. And Alan told me that this is the way you find the holes in your reasoning, is by writing. And I really believe that's true. Alan also said, whatever your idea is, it doesn't exist until it's in software. And the software should be fast. In fact, when graphical user interfaces and lots of things were coming in, Alan always kept the emphasis on people are going to want to do bigger and bigger and harder problems. If you sacrifice speed in order to do these other things, you've made a mistake in the long run. And finally, drive your research by what needs to be done, not by what you know how to do. We as academics are very tempted to do the next result because we know how to do it. Alan very much emphasized what does need to be done and then work over time to figure out how to do it. And we published a paper on that, Dave Goulds and myself and Tracy Opicka, who was a student here, a ranking and selection project, experiences from an industry-university collaboration, where we talked about the different objectives of academics versus practitioners and how those things can work together. And I've always kept that in mind when I drive my own research. So, I was very privileged to be at Purdue at the beginning of the simulation movement. Faculty, Pritsker, Schmeiser, Roberts, Jim Wilson, who was a student here, came back shortly after I left. Lee Shrubin came here on sabbatical, bringing Dave Goldsman, who were tremendous influences of my career. Everybody who was anybody in simulation came through Purdue. You just had to. Many of these are Bruce's students, but a tremendously active group of PhD students. Jeff Tu, Larry Lemus, Varadas Kachavichianakul, which I wrote without looking how to spell it. Kibam Kang, Jim Swain, Wang Yin Song. It was amazingly active intellectual time in simulation, that folks were challenging each other, talking to each other, and pushing each other to do better. And Monday night simulation, once a month, at Bruce's house, or at Alan's house, or at Pritsker and Associates, graduate students, faculty, visitors from the outside, talking about simulation, often at Bruce's house with the overhead projector on his pool table, talking about simulation issues in an informal atmosphere, and that was just tremendously stimulating. And that 580 course has echoed in every course that I have ever taught. I still do things in a case-based way exactly the way Alan did, both at Ohio State and my courses at Northwestern. Alan provided advice to me as a student. He was a role model and later was a co-collaborator on an NSF grant with Dave Goldsman and me. So in every single way, he had a tremendous influence on my career. So thank you very much, and thanks, Alan.